Okay, chapter 11, liquids, ooh, that's dark, solids and intermolecular forces. So this should seem much friendlier compared to what we were just talking about. Okay, so water, no gravity. This is a picture of some water on a space station. It's just a glob of water, there's no gravity. So we're going to watch this video. It's a different video.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung-out cloth? So, and had you used equipment that was here on board the space station, we might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today.
Look at his watch.
And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merit and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I fill a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
Isn't that crazy?
It's coming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of doesn't stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer in my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Okay, was that cool? That's not what you expect water to do, right? So we're going to talk about how that happens. Why does that happen? So here's a picture from your textbook of a big glob of water in space and someone touching it. And you see that it just kind of sticks to the finger, right? And kind of starts to pull away. This glob, my pointer's acting up now. This glob is very irregular in shape, whereas the one in this picture, yeah, it's all delayed. This picture is perfectly round. What happens if you've got droplets of water in space is you can kind of push them together. When they get close to each other, they will merge into one drop. And initially, they'll just be kind of like a blob of Jell-O and be all jiggly and irregular. But if you leave it undisturbed, it'll settle down and make a perfect sphere. And this is because the molecules of water are attracted to each other much like magnets are. And they are moving within the liquid, but if you leave them alone, they will settle into the sphere to maximize the interactions, the attractions between the water molecules, and minimize the surface area. And so that's why they make a sphere. The reason this happens is intermolecular forces. The attractive forces that cause water molecules to stick together in space are intermolecular forces. And these forces exist between atoms and molecules of all kinds. They are significant only at very short distances, but they are responsible for the very existence of solids and liquids. If there were no intermolecular forces, there would be no solids, there would be no liquids, there would only be gases, just random gases. See what my iPad's doing? It's showing me different things, but I can do the pointer. That's just fabulous. Not very helpful. Oh, there we go. Sometimes you just have to talk about it and then it'll straighten itself out. So the state of a sample of matter depends on the relative strength of the intermolecular forces compared to the amount of thermal energy. So if you have a lot of thermal energy, that means the particles are moving a lot, not necessarily traveling down the highway, but moving a lot within whatever phase they're in, solid or liquid or gas. And then if they're moving a lot, they may have enough energy that they can overcome those forces of attraction, the intermolecular forces. So let's stop that.